turn it off. Bad move. There we go. Pilot error.
He didn't do it. He did. He turned it off, so he turned it back on.
Come on in and shut the door.
Okay, welcome everyone. Good afternoon. Thank you for coming. My name is Ezekiel Garcia.
I'm Weston Velocity.
I'm Alexander Sulia.
And I'm Alex Xavier Huggins.
I'm Evan Brown.
This is our final presentation over the development of the secondary seal station. So first off, let's talk about why we're all here today. This is, like I said, our final presentation for our standalone secondary sealing station for our client, Johnson & Johnson MedTech. They are a company here in town, really all over the world, but they have a big manufacturing plant here. They specialize in making products, medical products such as sutures. We're going to present the fabrication process of our design of our machine. So this is our presentation outline. We have it split into 3 systems: the introduction, subsystems, and the conclusion. Yeah.
All right, first we're going to get into the current process currently in state at MedTech. Currently, MedTech uses two different departments to seal the sutures. So one department is going to be primary seal department, and the other department is going to be secondary seal, which you can see in the pictures. Primary seal is our client, so we're trying to replicate the secondary seal. And usually with the primary seal station, defects occur with the gripper chains that are used to pull it through the mass production seal stations. The misalignment can occur, and it'll cause improper seals and production downtime. All right, next we have our problem statement. The main problem that MedTech has is to test the primary seal. They have to completely shut down the secondary seal machine to make sure the primary seal is correct. And then why is that an issue? This facility produces about 1/3 of the amount of sutures in the whole world, and any downtime leads to a decrease in product output. All right, next we have our project scope. So our team was tasked with designing and fabricating a standalone secondary seal machine to be used to test primary seals for the primary sealing department before the packages moves forward to sterilization and final seal.
So we're getting into our client requirements. It is noted that certain parameters can't be disclosed just due to confidentiality, but our machine did have to meet 3 requirements. The heaters must reach a certain temperature in order to seal the package. Our press has to run at a specified dwell time. Our pneumatic cylinder must reach a certain pressure. In addition to these requirements, the machine also had to have a digital display just to display all the parameters and make sure they're met. In addition, the machine could not be hydraulically driven, so it could have been electronically or pneumatically driven. It must meet all OSHA Cat 3 safety guidelines.
So Johnson & Johnson tasked us with meeting 2 basic material requirements in our design. The first being that all materials that come into contact with the suture packages have to be made with medical grade stainless steel or medical grade aluminum or non-degrading plastic or silicone. And the second requirement is that all structural materials must be corrosion resistant and must be able to withstand all the applied loads during operation.
So since this was a pretty large scale project, we decided to go divide all of this into 6 different divisions or systems. We had our pneumatic system, our machining, our frame, PLC software, electrical, and safety, with all of them having their respective subsystems. So here we have an image of our completed machine. Just to go over the subsystems and where they're located. We have our load cell. They're located at the top inside that load cell housing. Our interlock switch, which is actually along the outside of the doors. Our insulation plate, which is actually covering the front of the heater die as well as sandwiched between one of the layers. Our bottom die, which is at the bottom of our die, or our bottom of our press. our pneumatic cylinder, which is actually located down below, right there, compressed air tank, which powers all of our pneumatic stuff down here, our transformer, right there, emergency shutoff in an accessible place right here, our evacuation station, which takes up most of the right side of our machine, our enclosure, which is located all around the machine, then our HMI, which is actually on that mounting arm right there. Then continuing this, we have the back side of it, where you can see our 480 volt panel is on the left side, our 240 volt panel on the back, and then our 24 volt panel on the right side. Then here we can also see the temperature transmitters, which are actually located along the edges of our enclosure. And then our top heated die, which is seen right there.
So now we're gonna get into the fabrication process of our entire machine. We're gonna go through each system one by one. These are just some pictures of the time we spent, working on it. There's Alex welding that plate there. Me cutting our the Lexon, so for our enclosure. That is a picture of whenever we finally had all of our enclosures, our transformer with the top plate all mounted on the frame. That's just a picture of us using a bandsaw to cut some metal. That is a picture of our one of our flanges in order to mount the plate. And that's our lab tech, Elijah, milling some parts for us. And then this is actually a picture at Ethicon where our big top plate is in the middle. So the first system we're going to talk about is going to be our safety measures. And the biggest one we had was going to be our safety enclosure. So it's a full 360-degree enclosure made out of Lexon and 80/20 rail system. And so it all connects together to make our enclosure, that's what we have mounted to protect the user from potential burns or crush hazards. It's not on this picture, but right here on the front of the doors is where we have our interlock switches, which is just essentially a door switch that prevents the user. So you can see here that it's green when it's red. So when the doors are open, the lights turn red, indicating to the user that the machine's not usable at the moment. In order for it to turn green to be able to use the machine, you have to close the doors, which ensures that the user isn't going to get injured. So the safety enclosure is one of the very first projects that we were able to work on due to material. We weren't able to get the materials we needed when we needed it, but this was one of the first ones we were able to get. And so we were given these essentially doors and other frames from Johnson & Johnson. And so we were tasked, we had to, because these doors, they were made, for their machines the way they use them. We had to take these apart and we had to modify them to make them our own to be able to fit on our machine. And so all the pictures here on this side, like I said before, this was one of the first things we had, so we didn't have any real raw materials to work with. We didn't have a frame. We didn't have our top plate yet, or our table plate. So we had to really go off dimensioning, and this is where I kind of drew out everything, to scale of what we needed. And so from there, we were able to take apart materials and cut them what we need, and we could build the enclosure. And so this is finally, down here, this picture on the left, when we got our table plate, all the pieces that we cut, we can kind of fit them together, just to make sure that everything was fitting the way we wanted it to. Once that was, confirmed, we finally were able to build our enclosure here, which this picture was taken a little further later on after we had it built, after we had put on our HMI arm and then the HMI enclosure with HMI. And so with that, we had, our interlock switches, we had to make plates for to mount onto our enclosure. This picture here is just, when we finally got our frame built, we got the parts back for that. We test fitted the whole enclosure on the plate to make sure it fit all the way we needed it to. In addition to those two safety measures I already talked about, we had an insulation plate here, which is a fiberglass epoxy laminate. And so that is actually in between our top die there, our load cell transfer plate, and our top plate there. And so what that does is it insulates the whole machine. It protects the user as well, but it insulates the machine is the main priority, because up here is where we have our load cell. And so we don't want that to get too hot, because the way that reads is through resistance. When you increase your heat, you increase your resistance. That can throw off your force readings. And then to protect the user, we put a whole piece of insulation on the front of, the whole press. So that way when you're changing out your packages and everything, you don't accidentally touch the die and burn yourself. In addition to that, we have, just some basic warning stickers, pinch point to indicate, potential crushes, heat, stickers, just potential burns. And we have 480 volt stickers to indicate that these are the high power parts on the machine. Finally, we have our emergency shut-off switch, which Alex mentioned on the side of the enclosure. That is, when it's hooked up to the 480 power, that when you press it, say something goes wrong, you press it, completely cuts off power to the machine, making it inoperable. With that, we have an emergency dump valve, which when you press the emergency stop, that's gonna dump all the air from the system. So your press won't run, your evacuation won't run, none of that will run. So if something happens, something gets caught, at least your piston or nothing's gonna move. To conclude all the safety measures, some challenges we had were, which like I said before, this was the first system that we were able to work on. And so we had to design really the enclosure without the rest of the machine. So that makes it, kind of hard just because you don't exactly know what you're working with yet until you get what you need. With that, we had to get a thinner insulation plate just because our tolerances on our rails with our top die and everything on the top plate, it was too thick. So we had to get a thinner one just to make up for that. We also had to design and make the plates for the interlock switches, the door sensors, and then had to make a plate or mounting bracket for the e-stop. If we were to do it again, I'd recommend, if it's possible, if we get the materials first, build the frame, build the machine how we want it, and then go back and make the enclosure just because you can design the enclosure around the machine. I'd also, take into account further our measurements and clearances, just so you don't have to go back later on, make revisions, mill things down, get new plates, whatever, and it works the first time.
All right, now we're gonna move into the operating system for our machine, which comprises of our PLC, safety controller, and HMI, otherwise known as touchscreen display. For those of you who don't know what a PLC is, it is a computer basically capable of receiving inputs from our field sensors and our safety equipment, from our safety controller as well, and also capable of sending the signals out to control our machine whenever selected by the touchscreen controls. For this project, we decided to go with the Keyence lineup. Keyence offered the best integration possible with a simple communication setup through Ethernet connections. And specifically with PLC, we went with the KVX 500, which is the latest model they offer, which paired nicely with our Keyence safety controller, the GC1000. This integrated directly with our interlock switches. And then we went with the Keyence VT5W07 touchscreen display. All of these, the touchscreen display, the GC controller, all connect to the PLC via Ethernet connection, which is streamlined, does not have to rely on Wi-Fi, so there should not be any outages depending on those connections. And then lastly, we went with the Invent Hoffman suspend system for the HMI arm, which is mounted on our safety enclosure. This allows for the user to manipulate the screen and control the machine in all three directions and streamline the operating process. So for the PLC side specifically, we needed two modules to run our machine. First being the analog input module. This takes all the field sensor readings for us and communicates them with the PLC and the rest of the system. So here is a wiring diagram showing the two temperature sensors on the left here and showing their respective terminal inputs on the actual module itself. And then here is the load cell amplifier and load cell along with their respective terminal inputs on those modules. And then moving on, we needed the digital output module, which is actually sending out the signals to turn on and off certain components in our machine. Starting from the top, moving left to right, we have all of these output signals coming from the actual module itself, which the first three here on the left are signals to our solid state relays, which run on 240 volts AC. The 24 volt signal switches those on and off like a light, and powers on and off the heaters if need be. And then here at the bottom, we have our solenoids, where the signal comes in and turns on and off the signals if need be. The relay bank that we are running the solenoids off of supply the actual power to run these components rather than the actual module itself. So here's showing the essential setup for the KV Studio software that I use to program the machine. This is a function block here, which sets up our timer mechanism. This includes ladder logic and structured text here in order to create that operation. And then here's the safety controller software. This combines the interlock switches readings and the redundant backup switch on the actual HMI that ensures that the user has closed the doors. And then here is the HMI touchscreen display software showing you a basic configuration of what we were dealing with the programming. So overall, main challenges with this process was that I don't have very much experience with industrial PLC programming. So the huge benefit with using Keyence was that they offer free technical support. So hundreds of calls, Teams meetings were necessary in order to learn the KV Studio, the VT Studio, and the GC configurator software. And as well with setting up an Ethernet IP bit mapping setup. I'd never done that before, and they were very helpful in that process. And we were able to overcome it. And then my last recommendation through this process is to have Johnson & Johnson, whenever we hand the machine over to you, to look over and review the programs and make whatever necessary adjustments that are required.
So next up, our frame. The frame is basically the premise for everything. It's going to house everything. We're going to store everything, and it's just going to hold everything, all right? So starting off with the table plate, we went with a 6061 aluminum plate. Originally, we had chosen a T304 stainless steel, but after talking with Tom, the machinist, the head machinist over at Johnson & Johnson, he had suggested we switch over to aluminum. It was a great option since it was cost effective. It still maintained that sterility needed for the whole project, and it provided the necessary space and strength for the whole machine. Then next up, our support rods. So our support rods are right there. They're basically what hold our press assembly together. It's also where the bottom die actually slides on. As y'all can see right there, we have these self-lubricating bushings that help the whole bottom die move up into that top die. We had originally gone with T304 stainless steel again, but we got a great suggestion by Tom to use Thompson steel. So Thompson steel is still stainless steel, but it provides, it's a lot smoother. So whenever you're actuating on it, moving up and down on it, it's still going to maintain that smoothness and allow for easier flow of the machine. Next up are legs, bracing, and storage. So originally we had gone with 1-inch aluminum square tubing, which after consulting and going back and forth with Johnson & Johnson, they kind of threw out the idea of us using 80/20 T-slot aluminum rail. We hadn't thought about that at all, but after they brought it up, we realized it was a great option as it was weight effective compared to steel, which in our previous iterations we had kind of steered towards. It still provided that rigidity. It was very modular, so we were able to take everything apart and put it back together, versus if we would have made everything out of square tubing, everything would have been welded together. And then the rails came in, they were very helpful as they allowed us to put our panels, our air regulators, emergency stops, and mount different items onto our machine without having to take up more of our storage space. And then talking about our storage, we went with flattened expanded 3/4 inch number 9 steel. So the reason we went with flattened expanded steel was the strength to weight ratio, and it's commonly used for shelving as well as its cost. We knew that one layer of flattened expanded steel wasn't going to be enough, considering we have a 250-pound transformer and then air tank down there. So what we actually decided to do was stack 2 layers of that and then put railing in between them. And I actually welded all that together. You can see the little marks, and since it is regular steel, we clear coated everything just to ensure it didn't corrode over time. And here are some more fabrication pictures. Here you can see when we were putting all the panels on there, you see Wes cutting out all the expanded steel. Here's our kind of frame, once again, put all together. Wes having fun inside the frame. Now, we actually did this to test to make sure this bottom rail wouldn't slide further down, and obviously it held up. And then there's me welding up those 2 layers of expanded steel together. So, once again, the review for the frame. Challenges we faced were fitting components together, working with different materials, fitting large components into small spaces. Fitting that transformer in there was a multiple hour kind of figure out different angles, trying to do something, because yeah, it was very hard to fit in there. We had to use a engine hoist in order to move the whole transformer in there. And then changes in material selection as the project went. I do want to note that for the things we did use regular steel for, we still clear coated just in case, just to make sure it's corrosion resistant. And then recommendations, once again, we want to have Johnson & Johnson review all the structural components to the machine to ensure its integrity. Next up is the pneumatic system. So the pneumatic system is what basically drives everything, anything from moving actuator cylinders and our actual vacuum. First up, kind of the big boy, the pneumatic cylinder. So this is what actually raises our bottom die onto our type die, and then reaches that specified force, dwell time, and then that top die is what reaches the temperature. We went with an ASCO Pneumatics X38W series. So this cylinder, once again, is what raises that bottom die. It's easily replaceable, it's easily workable, and it easily integrates into our system. As you can see, these tie rods at the top allow us to just bring in the cylinder from the bottom, raise it up, and put nuts at the top in order to secure it onto our machine. And then, as y'all can see right here, it actually has a threaded end. This is what we made a flange for. So we made a flange in order to attach that cylinder onto our bottom die. The next up, the solenoid valve. So the solenoid valve is what actually controls all the motions for our pneumatic system. So it does it for the cylinder, the evacuation actuator, as well as our vacuum generator. This specific one is great since Festo is a trusted product that Johnson & Johnson currently uses, and it easily integrated into our PLC, our whole Keyence system. Next up is the air regulator. So we went with the Festo MS4 air regulator. This is what regulates the pressure going to all of our components. From we were told plant air at Johnson & Johnson is around 140 PSI, and if we ran 140 PSI for all of our components, stuff would definitely go wrong. And so yeah, this is what we use to step down that air going to all of our components. I can't actually say exactly what pressures we're running, but all of them fall within our ranges. And once again, this is a trusted product by Ethicon, so there would be no issues with that. Then next up, our evacuation station. So our sealing process is actually a 2-stage process where we have an evacuation station that removes air from the packages, as well as the one that does the secondary sealing. The evacuation station uses that pneumatic actuator right there. What that does is actually lower our vacuum source onto the package and then removes the vacuum off of it as well. This is one they currently use for their current evacuation process, so we know it's a trusted product. And then it's easily maintainable. All you need to do is grease the sliders on it every once in a while. But yeah, it's pretty straightforward. It also uses the same connections we use for our whole pneumatic system. Our whole pneumatic system runs off of 8mm quick connect. So these blue lines right here, they're used for the whole system. Next up is our vacuum generator. For those of y'all who don't know, vacuum generator actually uses a Venturi effect in order to create a vacuum. We'd actually seen it originally in their primary sealing process. They used it to move packages around, but we decided to kind of reverse engineer it and use it as our vacuum source instead of having a vacuum pump in our system. So all this does is it runs air through this nozzle right here, and it creates a vacuum through that top port. It meets our evacuation standards, so it reaches that vacuum strength we need, and then it uses our onboard air supply instead of having to supply a whole vacuum to it. Here's kind of another fabrication picture of our whole pneumatic steps. You see our air regulators are right there and labeled for all the parts to be, or for you to know what you're actually changing. Our vacuum generator, once again, there's our whole tank with our emergency dump, our gauge, and our solenoid valves right there. Another close-up picture of our solenoid valves and then our actuator, as well as the vacuum is actually running right in the middle of that suction cup. Here's a basic pneumatic diagram of the whole pneumatic system. So you see our air is being supplied into our air tank with an emergency dump just in case. We have this then go into the regulator banks where your pressure is set, and then they are all ran to their respective solenoid valves, which then actuate whether you want your up and down motion for your pneumatic cylinder, your vacuum to be on or off, or your actuator to come up or go down. Then, since we are talking about the pneumatics, we want to talk about the actual secondary sealing press. Here you see our cylinder. It's actually an 8-inch bore with 6-inch strokes. So those of y'all who don't know, it's pretty big. It's, you know, if you're small, you definitely won't be able to carry it. But here we have some of the parts we had to custom make. We have our load cell transfer plate right there. This is actually, so we faced a little material problem with that one, where that one's actually A36, the whole base of it, and then I guess the rod sticking out of it was actually A2 steel. So we had to go through a whole process in order to weld it. We had to heat up both elements in order for them to be pre-tensioned, that way they won't crack. There you can see our bottom die, and here is a great picture of our actual press, the top of our press. You see the heater die is at the bottom, our insulation is sandwiched in the middle, and then our load cell transfer plate is right there. And here's the whole overall picture of the press. Just to kind of review everything once again, we faced challenges with sourcing machining. That was definitely a hard part for us. We were under the impression we would be able to do a lot of it here, but after going through everything, we realized not everything is feasible to do with our limited resources. Port identification with some of the solenoid valves. Fittings, we had to get some last minute fittings that we didn't know we needed. Part delivery, miscommunications between ourselves and the machinist, custom parts that had to be made, and then tapping and threading some of our holes. Then once again, recommendation, Johnson & Johnson should review all the pneumatic components before fully integrating the machine.
Alright, so next we'll be looking at the electrical side of the whole system. So for our machine, we will only be needing 240 volts of alternating current, and that will be powering the heaters. But Johnson & Johnson will be providing 480 volts of alternating current. So we needed a transformer in order to step that down. So we're using a 3-phase transformer. This is in order to step that power down for the rest of our machine. So again, we had to lower even more to 24 volts, so we are using a power supply. And this will step down 120 volts into 24 volts of direct current. And I'll explain how we got 120 in a second. This will be outputting 20 amps of current. And we determined that because our 24 volt components are drawing around 16 amps. And in order to safely operate those, by the National Electric Code, they recommend 1.25 times that amount of current. So that's why we went with 20 instead of 16. We are using 3 breakers throughout the system in order to add some protection. The first one is a 15 amp breaker. This one is where the 480 volts will be directly plugged in. This will prevent overload of current flowing through the system. The next one is a 10 amp breaker. This will come after the transformer, and this protects the transformer itself from the power supply or heaters drawing too much current and damaging the transformer. And then the second one, the final one, is a 10 amp breaker, and this also comes after the transformer is used to protect the power supply. And this one is only a 1-pole because our transformer uses 1-pole power instead of 3 poles for the higher power systems. So we're also using solid state relays. These are basically power switches which are used to control the heaters. So the PLC plugs into the solid state relays, and controls that 240 volts being switched on and off for the heaters. And that PLC reads temperatures from our thermometers and the die, and will switch on and off the solid state relays which control the heaters. And then here we have our contactor. This is wired into our emergency stop. So if the emergency stop is pressed for any reason, this will shut off power to the whole system. And this is placed at the very beginning where the 480 volts comes in. So these are some pictures of our panels. On the far left, we have our 480 volt panel. So power will be wired in through this breaker right here, the 480 volts, which will run into the contactor, which shuts off power if needed. So from there, it goes into the transformer where it is stepped down to 240 volts of alternating current, and then we'll run into our 240 volt panel. So it'll run into the breaker here, which then powers all three of these solid state relays, which run into our heater bus bar here. So this takes 3 lines of power in order to power all 4 of our heaters. And in this configuration, these pictures, we don't have power running into a 480 volts because for testing purposes and for what we have available, we only have 240 volts, so we have it directly wired in here into the wall. So our transformer isn't in use, but we did testing on the system to make sure it works. And then this is our last panel, the 24 volt panel, where most of our components are. So this is the power supply, which changes our 280 volts down to, or 240 down to 24 volts. And then from there, it runs into a positive and negative bus bar, which are used to power the rest of our components. So we have the PLC here, our load cell amplifier, our relays, which power all the solenoids for airflow, and the emergency dump. And then our safety controller, which takes inputs from our safety fixtures controlled by the PLC. And we did a lot of cable management because we have a lot of wires going on, so they're all zip tied, and we have labels on as many wires as possible to make it easy to understand and for Johnson & Johnson to be able to work on it. We also have, you can see a little here, cable sheathing on the, for wires that are outside of the machine. We have just plastic cover wrapped around them so wires don't get damaged if it's moved. So this is a wiring diagram for the whole system. You can see we have 480 volts coming in. It gets stepped down here on our transformer to 240, which is used in the solid state relays in all 4 of our heaters here. And then that goes to our power supply, which is changed to 24 volts of DC, which will power all the rest of our smaller components. Some challenges we had with this whole system is we are not electricians and haven't worked on industrial wiring. So we outsourced a lot of information with multiple contacts. And then we also had Angelo State Facilities and Management, the electricians, we had like 6 of them come out and inspect our entire machine, check all the wire connections, the flow of power to ensure everything was safe to operate before we turned it on, and all the grounding we had. Some recommendations we have is for Johnson & Johnson electricians to validate all of our wiring, make sure all connections are good, especially after transportation of the final product, and then have them review and update any wire diagrams as needed.
All right, now we're to our sensor systems. First, we have our load cell. Our load cell is used to measure the pressure on the package directly, since there could be blow-by or drag in the cylinder. And then this load cell does meet our force specifications, and this load cell did require an amplifier, so we included that as well. The amplifier is used to regulate the voltage into the load cell, so it doesn't fry it, and to also boost the small electrical signals sent from the load cell to our PLC, so it can be read accurately. Next up, we have our RTD probes, and RTD probes are thermal sensors, and they're used by measuring the resistance through the wires with the temperature change, and that's how you get an accurate reading from those. We have them set up on each corner of our die. Oops. We have them set up on each corner of our die right here, and it's measuring an average temperature across our heated die. And then these are trusted brands with Johnson & Johnson. The RTD elements are delicate and can be damaged easily, so we did have to create our own 3D casing. We did design and create that. And we also had to be very wary where we put our cables at, so they don't get damaged at all.
All right, so moving into sensor calibration, we're gonna start with the RTD transmitters themselves. Basically, those RTD transmitters are taking the feedback from the RTDs, those resistance values, and then converting that to a 4 to 20 milliamp current reading, and the 20 milliamp being our high value, and the 4 milliamp being our low value. This process took about a week. I initially thought I had fried the RTD transmitters through the calibration process. I tried ice baths, all kinds of different methods, and it actually ended up being that the multimeters were not reading properly and our wiring was not set up. In order to give Johnson & Johnson the best product that we could come up with the resources that we have, we had to refer to an engineer from the distributor company of these RTD transmitters to essentially simulate the resistance values for these temperatures. So we actually took inline resistors and simulated temperature values in order to calibrate the sensors themselves. Whereas with the actual load cell amplifier, that was pretty straightforward. That came with the instruction manual. Basically, we used a simple method of simulating the resistance value that comes with the data sheet, the voltage value, sorry, that comes with the data sheet of the load cell that approves that it operates properly. So we just simulated that maximum voltage and our lowest voltage and set that to our positive 10 volt and negative 10 volt reading for our analog input module to read.
Right, and then the challenges for the sensor systems was calibration, because we didn't have any experience with calibrating those. And also we had to design and print the 3D housing for the RTD transmitters. And then our recommendations would be for J&J to validate the calibrations that we already did on the load cell and the transmitters. And then also to maybe move the RTD transmitters into a more secure casing in the 24 volt panel.
So I know we've been talking a lot about the whole machine and different parts. You're probably bored out of y'all's mind. But we're gonna go over the whole machine process just to see how everything kind of works together. So here you see Wes opening the doors, which breaks those interlock switches. You see it turning red. On our evacuation station, as well as our press assembly, we actually have two little rods sticking out that allow you to align the package on there. If y'all have the package, y'all see two little holes on them. He goes over the HMI, resets the door lock, which is very important, and then starts our evacuation process. You see it lower on there, and it had that suction cup on there that actually removes the air from inside the package. You then open the doors, remove that package, and move it over to your actual secondary sealing. So once again, you have to align those pins on there just to make sure the package is straight. Close the doors, ensure they're green, and also reset it on the screen. Then you go over to your secondary sealing and you begin that process. Those are actually our guidelines right there. You see it come up, it reaches the specified force, and that's when the timer starts and it begins that dwell time. Once it reaches our dwell time, the package lowers, where you can then open the doors and remove the package.
So overall, we had a lot of challenges completing this project over the last 2 semesters. For this semester, one of the big ones was part delivery. Getting all of our parts created and machined in time was also a big problem, but getting Johnson & Johnson was luckily very helpful with delivery, getting all of our components ordered and delivered to us in time for us to make an actual finished product. For machining, like we said, we initially thought we could do most of this in-house, which we could not at all. So for parts such as this plate here, we sent files over them where they used their own machine shop to create those and get them delivered to us, so that was extremely helpful. Capabilities and know-how, this is a very large project with multiple things we haven't done before, but with multiple outsourcing, plenty of phone calls, we were able to figure out what we needed to know and get a final product delivered. And then with oversight, we had not a lot of professional oversight, so we kind of missed some small details throughout the project with our initial planning and designing, which ended up coming back to hurt us a little bit, but we were able to overcome all those and get a final product done.
All right, and then now we'll go over what we would do differently We would definitely outsource the power delivery from the jump and get past all that trouble. And then next we would have planned to outsource a lot of our machining, because we did, like Evan said, we did plan to do some of it ourselves. And that could have maybe pushed along our schedule a little better if we already planned to machine it outside. And then also material selection. Some of our material was hard for J&J to machine, and they had some difficulties there. And also with material selection, we would also have went with that, with the frame that we went with now, originally, because of how easily it all came together. All right, and then next we have our cost breakdown. So about half of our pie is gonna go to our machining, so that's around $25,000. The second biggest slice is gonna be our PLC and HMI, that's gonna be around $14,000. And then after that, it's gonna go to the frame, which is about $7,000. And then our total cost of the project came out to be $59,902.84.
So we'd like to extend our appreciation to these specific individuals who helped us get through this process. First being Ryan Romaneda, who's our primary contact at Johnson & Johnson. He helped us get through some of our big struggles and helped deliver everything that we needed in order to get this done. Next we have Tom Campbell, who's a machining contact. He's the machine shop supervisor over at Johnson & Johnson. He helped us get out of the bind where we didn't know who was going to machine our parts because we couldn't do it in-house. So he was very helpful and helped catch some mistakes in our design and helped us work through them. And then we have Jeff Roberts, who is a master electrician who works on industrial equipment. He offered his personal insight and helped us walk through the whole power delivery design. And Keen's tech support team, these guys saved the whole project. They a whole lot of time spent with these individuals, and they helped us get through it. And then ASU facilities management electricians, these guys are kind enough to come out and test our whole 480 power delivery and all the bonding on our machine to make sure nobody were to get electrocuted if we were to go ahead and hand it off to Johnson & Johnson. They also helped us set up that 240 volt three-phase plug so that we could actually just test it ourselves and unplug if need be, gave us that functionality. And then Donald Datton, an engineer out of Palmer Wall, he helped us with a lot of information on those RTD transmitters when we were struggling to get those calibrated. And then Dr. Hawk, who was our primary professor who oversaw our whole design process for this project. Mr. Brasher, who helped us with some of the sensor calibration. Dr. Garcia, who helped us the last semester with our FEA analysis. And then Dr. Bassini, who gave us a lot of helpful insight on our machining in-house. And obviously, Mr. Gravely, our lab technician, he helped walk us through all of our machining that we did in-house. And then Elijah Garcia, a Hunter Strain Engineering lab assistant who helped machine some of our parts for us.
Thank y'all very much for coming today. Now we'd like to open up for any questions.
We got a lot of subsystems or part selection that were like preferred vendors, preferred systems from J&J, so which makes part of your engineering design really easy. So how much of your selection how much of your solution was based on that? I mean, there's nothing wrong with that.
Sure.
How much of it did you actually have to go through? Okay, well, we do have like a wide open path to select this system or subsystem, and what were the parts where you had we had more leeway in the design, and where you guys were actually doing more of that system selection?
Yes, sir. So for pretty much the whole machine, we try to use as much of what J&J currently uses, just because it's easier for them to work on.
Mm-hmm.
But then some of the other ones, last semester we actually did a design matrix where we provided at least one different alternative option for every single component. And based off that and some of the feedback we got after the presentation, that allowed us to conclude what we were going for. Definitely the systems for the pneumatic were kind of straightforward. Originally we had gone with a different PLC system, but that got changed. Just different things got changed at different times. There was no set, I guess, I don't know if you wanna.
Yeah, with the PLC specifically, we were gonna go with an Allen Bradley system. We were told by Johnson & Johnson that Keyence was a better route because of the free tech support. So that basically helped get that weight off the shoulders. We could just directly call in and get the help that we needed with the programming. With the sensors and everything else, that's pretty much stuff that was coming directly from them in their inventory.
I'd say probably one of the biggest parts that had the most leeway in design would be the enclosure. I mean, originally we had a design where it didn't have a top, it wasn't fully enclosed. The way we were gonna attach it didn't make a whole lot of sense. Looking back at it now, you know, now it's a lot more rigid. If anything was to happen, say, you know, say the machine was to fall over or something like that, you know, that enclosure, it's gonna protect the machine, but it protects the user, you know, there's no way to really, as long as those doors are closed, there's not a whole lot of way to get injured, other than maybe, you know, something electrical goes wrong, but from the press itself, from getting burned, from getting crushed, with that, now, there's really no way for anyone to get injured with that.
The only way, I mean, your hand gets crushed, when that cylinder goes up, it takes around slightly under 3 seconds to go up, so if you can't get your hand out of there, that's kind of a
Machine won't
personal
run.
problem.
Machine
Yeah, it
won't
won't
run.
run if it's open either way,
It's the
but.
whole safety system.
Yes, sir.
Yeah.
But, and also the whole electrical power delivery guys, that was, I mean, 100% on us, and we had to outsource all that information to get that, and, I mean, those components were straightforward once we were in contact with the electrician to get that design. That's pretty much overall how it went.
So did you solve the problem? Did you solve the problem that you were like?
Oh, it seals packages exactly how it should.
Okay.
Meets all the required.
Yeah,
sure-
I calculated dwell time there, it's like 1.7 seconds, that's, but, no, I don't.
We actually ran the video and checked the time on that, did the playback, and
It matched up
it
with
meets
whatever
our
numbers are
required.
supposed
Can you go back to the video when it's working?
I have a question about one of your design choices there.
So when you are like putting the stuff in there, it seems like you have to like put it carefully, or it will just go like.
So it has those little pins sticking out. I don't know if the packages are still out there. You can see 2 little holes in
There's
the
registration pins on the package.
Here, I'll show you.
those 2 holes.
Okay.
So those 2 holes here in the center, we have pegs that line up that
So
package.
you have to just to go on.
You just have to put it in there manually.
It's also aluminum foil, or it's foil, so you have to, kind of have to work it to get it lay flat.
Okay.
So, can you run it back? So I got a question about, I got a little ergonomics question about this. This may, I don't know if this is trivial or not. Okay, so you place this in this orientation for the initial evacuation, right? Okay. All right, and now you go to put it in the press,
You have to rotate.
and you have to rotate it 90 degrees, and I'm guessing there's a specific, so, was that a design decision, did it just happen? Because
if you want-
that strikes me as,
That's
it's
what.
not a
if you
major
want us-
thing,
if
but
you
then
want us to
that,
do-
you're now making an action where somebody can do it wrong, right? Where, instead of just taking it out and putting it in the same orientation, so, how did that happen?
In the instruction manual, it's actually, we say that you're supposed to put it on those pins, but this was actually a mess up on our part that ended up working out. I remember, I mean, if we're being frank with y'all, we got our last part last Wednesday. And we got that whole machine put together that day for the last part of it.
Can you get it to where it shows the press?
Yeah.
Yeah.
So originally,
Yeah.
the orientation was supposed to be for this to be rotated this way, so both of them would be facing the same way.
Right.
But I don't know what happened, we messed up on our drawings, but it worked out. It's one of those things that, I mean, the Lord was just watching out for us. But Yeah, originally we had planned for it to be fully symmetric to both sides, but, I mean, it didn't come out that way, but it still works.
Okay.
Future design.
Future
Might be
design, you
that
would
way
definitely
and
take that
alter.
into account.
Cody?
So how many of those are they going to be produced
So
per hour, or, I don't know?
this is for testing the defective products
Okay.
that come off the line, so it's not necessarily gonna be in their main line.
Okay.
So with that, with how the process is set up, I would assume, I'm just kind of giving it a ballpark here. I think you could go probably 3 packages a minute if you're efficient with it, like running the process.
I don't think at the beginning you explained I'm guessing nobody understood why Ethicon wants this device, because this is not a production device, right?
No, sir, it's
Right.
for, strictly for
Okay,
testing.
so why don't you try that again? Why does Ethicon want this device?
So,
And I'll give you a big hint, nobody here knows about primary sealing, secondary sealing. 90% of the people here have never seen that packaging before, they don't know what.
so this is basically the packages that Ethicon produce on a daily basis. Here they have in their sealing process, they have both a primary and a secondary sealing process, with a third buffer step being sanitation. So first they seal around the outsides of the packages, but when they're doing that outside package, this is actually on a conveyor with chains on it, and this pulls it through. The whole thing's automated. So things that go wrong, sometimes the tensioning on those belts is, a little off, so it causes crimps or defects in the packages. So once that defect is there, it won't fully seal. So that's what we had that machine for. It's gonna test that seal, and then, cause right now all they do is grab the package and throw it away. That's their only solution. Or, not really, they have to go over to secondary sealings and shut down that whole machine in order to test the package. So all this does is replicate that whole secondary process in one machine. That way, they won't have to go over, shut down a whole machine just to test one package.
Does that kind of make more level?
Well, I understand it, I'd have to have somebody else,
Yeah.
but I've been out there a couple
Rescue
times.
product that's been damaged, or is it just to test the sealing?
Possibly.
It-
Because you still need to sanitize in between, right?
Right, that's right.
You're not doing that.
Right. So, yeah, when these packages get brought over to our station, they will already be sterilized. Our evacuation is primarily just to shrink the air out of the package, make it small, make these pockets smaller, essentially. Is there any other questions?
When you open the doors, you have that red light, green light, does that actually stop
Oh, yeah.
the process? You can't run the machine when
You
it's
cannot run
just
that. You can't run that, and you can't run the machine without hitting the redundant backup on the touchscreen. So there's two fail safes.
So we do it 480 in the lab, so why, I understand, but so why did you decide not to use a 40 in the lab?
We need 483 phase. So right now, after discussing with the electricians that came in, we walked through and looked at all the outlets that we had access to. If we were to actually have a physical plug-in, there's
Okay, yeah, okay.
there's only 2-phase 480. That's the
Okay.
highest that it went to. So they had to do some of their own work in order to test the 483 phase, which I cannot disclose exactly how that went, but they did it. Cody?
Yeah, so I saw that, whenever you're actually putting it on the sealing station, I know you'll have these 2 holes, they have to line up the pins and anything like that. I get it, there's like some percent error on human error, on lining up those pins, but is there any reason that the actual package should not be in alignment? Is there any error in it? anything like that?
Those pegs are tall enough to where this actually sits directly on there, and their diameter actually is within like 1/1000th of I would say, of an inch of those holes. Does that mean there's really no wiggle room once you get it on there? Other than ensuring that it's flat, it's probably the best method. Is there any other questions?
You want to tell everybody what HMI is, since I would commend you in getting down a bunch of lingo, but I think you didn't always nail your audience here.
Yeah, so an HMI is a human-machine interface. It's another way of describing a touchscreen display.
So what is RDT?
Or TD.
RTD, I don't know.
It's a resistance temperature device, so it just,
Detector.
detector, right. It just measures the resistance on the actual probe.
It's a fancy thermostat.
Okay.
It's a linear relationship between resistance and temperature. So we essentially referred to the tables that were specifically for those sensors to actually interpolate those resistance values so that we could simulate them for our temperatures that we needed to calibrate our sensor for.
So you weren't actually calibrating to either temperature or force, is that correct? You were just calibrating to, you were setting up your, I don't know, it's your amplifier or your, but you were given the calibration factors for those and you were just setting up your system so that the output was right, but you did not when you go to calibrate this stuff in the lab, if it's a temperature thing, you bring it to a known temperature and then check your output, right? And the same thing with, you put a known force on it and you check it, but that's not the way, I'm not sure what you call, I don't know if I would call what you did calibration, but you weren't calibrating to force or temperature, right? You were.
Right, so we're calibrating to the best of our ability, and then we've actually.
You given the engineering units that was the.
Right.
Right, okay.
We plugged into the machine, and then we actually have, inset, like offset values in order
Right,
to.
so you're making sure-
To scale, to get it to, that validated actual.
Right, when
reading.
it's producing 0.3 millivolts, it's supposed to read 75 pounds, or you were getting 75 pounds out of your system, but you weren't putting 75 pounds at the end and looking on.
No,
Okay.
that's right, just simulating it.
Yep.
It's a simulation calibration.
So your project cost was $60,000.
Yes, sir.
What was that process like, and how did you get it funded?
We had a budget through Johnson & Johnson. They gave us our budget and we had to keep it as low as possible, which still our numbers are significantly less than they would have paid if they outsourced it to professionals.
Yeah, but how much did they pay you?
We're here for free labor. We're here for the experience.
Yeah. So what was the budget?
Started with $80,000.
Where's Ryan? How'd they do, Ryan?
I think they did very good.
You gonna use it?
We will, yes.
Awesome. That's all we need here.
In fact, this week would have been a good week to use it on the floor. Kinda need it right now.
Any other questions?
So how many, $60,000, so how much is it gonna save you? The first week you use it?
First week.
Yeah.
Well, that is a good question.
It's a good
It's been a while since I talked to finance, but I think my rough calculations, I think it should pay for itself in about a year.
That's a pretty good ROI.
More questions or comments, or we're open to suggestions too, anything y'all think we could have done different. That'd be great, greatly appreciated.
We are actually, after this, gonna go to Hunter's Train. We have it all set up, so we can go demo it. If anyone wants to come, we can take y'all over there.